My topic is going to be, or my general presentation is going to be on introduction to deep reinforcement learning. I'm going to try and make this beginner friendly. Unfortunately, some things are hard to explain without having the maths or the symbols in there. But I've tried to make this as beginner friendly as possible. And then at the end, we can have some questions. The general overview of what I'm going to speak about is firstly, why reinforcement learning? So why is this even a field that we are interested in? Why is reinforcement learning an interesting subfield of machine learning and what kind of problems it can solve? And then I'm going to go into the general flow for reinforcement learning and just a bit about the intuition. How do these reinforcement learning algorithms work from like a high level? And then I'm going to go into a bit of the details. So I'm going to speak about tabular reinforcement learning. So how does reinforcement learning work when you are working essentially using tabular data? And then I'll speak about Q-learning, and hopefully I'll be able to get to deep Q-learning at the end. So the first question is, why reinforcement learning? So it's a very good question to start off with. So the field has had a lot of breakthroughs. I could spend the whole presentation speaking about the breakthroughs in the field, but I'm going to just speak about a few of the notable ones. Firstly, AlphaZero. So this is a system that could teach itself how to master the game of chess, shogi, and Go, and actually beat world champions in each of these games. And the real interesting thing here is that there was no human knowledge. So the system learned by playing against itself in like a method known as self-play, and it eventually was able to beat world champions in the field. So this is AlphaZero. And then after that, we also had things like MuZero, which is, again, a system that learned to play these games, but without knowing the rules. So what I mean by the rules is essentially the dynamics of these games. So for example, if you're playing chess, you know the rules of chess, you know what pieces can move, you know what, if I take a pawn and I move it forward, you know what position the pawn is going to be in. But MuZero was able to learn how to play these games without knowing the rules. And the important thing about this without the rules part is that when we apply reinforcement learning to the real world, we don't know the rules. And this is sort of a big step to having like reinforcement learning algorithms be applied to real world problems. So I would say the next point is thinking about this beyond games. So I'm sure a lot of people have heard about reinforcement learning advancements in terms of games, and they probably have questions like, why should we care? Why should we care if reinforcement learning can play Go or all of these other games? Firstly, it's that games are just a good test bed for solving problems. So if you can formulate your problem in a way that it relates or looks like a game, I'll speak into more details about what that means. You can use these algorithms to solve real world problems. It's just that games are a good way to test performance and improvement in some of these algorithms. So if we look at some of the applications, so MuZero, what I presented a bit earlier, was applied to optimizing video compression on YouTube. There's a nice YouTube video and blog post on this. And day to day at InstaDeep, which is the company that I'm currently at, we use reinforcement learning to solve real world problems. So we're using it for train scheduling. We've partnered with Tessera, which is a German railway. And what we're doing is we've created this simulator. You can't see the simulator, but this like map thing over there. And what we're doing is we are training reinforcement learning agents to be able to do train scheduling. And this is a difficult problem because if you have many trains, you have many potential routes, so it must scale. You must accommodate delays, train breakdowns, so the method must be robust, and the trains must be on time. So this must be efficient. So this is just showing that even though a lot of the work in reinforcement learning is done on games, it can be applied to a lot of real world problems. And I'll explain in the next few slides how you can sort of formulate real world problems in a way that reinforcement learning can solve those problems. But first, I'm just going to start with the general flow of reinforcement learning problems and the intuition. So firstly, I'm going to start with the environment. So environment is the system we care about. So it returns a reward signal, but it's a system we care about performance on. And it's what our agent sees and interacts with. So in this example, the environment is going to be like a soccer field or a football field. And an agent is the entity that interacts with the environment. So this is the thing that interacts with the environment in some way. And also it needs to make decisions, it needs to adapt, and it needs to learn. So this is an agent. So if I had to put these two together, what you can see is we have our agent on the left-hand side, we have the environment. We see that our agent does something. So it takes an action from the available actions. That's all these symbols mean. It just means A is an element of the action space. So it takes an action from the available actions. So you can think about, I'll actually give a concrete example in the next slide. And then our environment returns two things. It returns the state, so what the field looks like, and it returns a reward. So it tells our agent how good the action that it currently did was, and this is sort of the general flow for reinforcement learning problems. And if I had to sort of roll out this reinforcement learning loop, this is how it would be. You have your robot, it takes an action, let's say it kicks a ball, and then it scores a goal. And because it scores a goal, it gets a reward of +1. And then the state of the field changes. So previously, let's say the field, you now have to reset back to the middle of the field because a goal has been scored. And then we follow this process iteratively. Now our agent sees what the football field looks like, takes another action, receives another reward. So this is the general iterative reinforcement learning loop that occurs. And just to make it clear, I'm also going to compare reinforcement learning to supervised learning. So I think there's been classes on like classification. So I think this will maybe help drive home some of the points that I'm going to make. So if we compare it to supervised learning, so supervised learning is one shot. And what I mean by that is I have an image of a cat. I pass it through some sort of classifier and I get an output. And the output can say, okay, this is a cat or this is a dog. But reinforcement learning is sequential. So if you saw like the previous slide, our agent was taking actions, receiving feedback. So this is like, I'd say, one of the major differences between reinforcement learning and supervised learning. The one is one shot and the other one is sequential actions. And that's why you'll hear of like reinforcement learning as being known as a thing to use for sequential decision making. So this is in terms of decisions. If we move on to how reinforcement learning compares to supervised learning in terms of how we train these algorithms. So this is just a standard supervised learning loop. You have a data set and then you feed like batches of the data set to a model and you get some sort of performance. So what are we using in the training process is this training data set, and this is labeled examples. So you have images of a cat and images of a dog, and these are labeled examples in our training set. So this is how you do it in supervised learning. In reinforcement learning, it's very different. What we learn from is actually an environment. So we learn from interacting with the environment. There's no labeled data. So if we look over here, we have this field. So this field has to return some sort of reward, It needs to have some possible states and actions. It also has rules and dynamics of a football field. So in practice, what you would do is if you have a problem, you would need something to act as a simulator. So you can think of like a virtual simulator, as opposed to having to have these labeled examples. So if you wanted to teach a robot how to play football, you would need some virtual environment that would run like a football game. So in reinforcement learning, you have RoboCup, there's, I think, Google Football. There's a lot of different environments where your agents can learn how to play football virtually, and that simulates, or hopefully simulates, what would happen in the real world. So another important difference is that in supervised learning, what we care about is performance on a test set. So we have our training data and we have our test data, and we want to know how well our model performs on this test set. In reinforcement learning, because we don't have a concept of a test set, what we actually care about is we want to maximize the cumulative reward. So again, reward, I'll speak a bit about later, but you essentially want to score as many goals as possible in a match, or you want to score as many goals over, let's say, an average of 5 or 10 matches. So we have different objectives in supervised learning versus reinforcement learning. So if I had to, like, let's say, summarize, this is a general reinforcement learning loop. And reinforcement learning is about goal-directed interaction. Goal-directed learning from interaction. So our agents learn through trial and error. I say goal-directed because you usually have to tell the agent what is the goal. Essentially, you can learn that from the reward signal, but our agent just learns through trial and error. And what our agent learns is it learns what to do. So if I am in the middle of the football field and the ball is far away, what should I do? So how do I map situations to actions? And we'll formally explain that like in future slides, but basically the agent wants to learn what to do. So to be a bit formal, I'm going to speak about tabular RL. And I need to introduce a Markov decision process. So again, there will be some symbols. And if you don't understand the symbols, I think that's okay. It's just important to get the intuition. And then you can eventually after you see the symbols quite a few times, you'll be a lot more comfortable using this terminology. But a Markov decision process is just a formal way to describe a sequential decision-making system. So previously, I spoke about this field over here. We need to formally describe this field and the properties of this field. So this is what an MDP is, or Markov decision process, allows us to do. And there's also this thing called a Markov property that just means that transitions only depend on the most recent state and action and no prior history. Again, if that doesn't make sense, I think the main thing to focus on is that the current state contains all the necessary information. So if we had to be formal about it, this is how we'd formally describe it. And if we had to describe it in text, it's just basically the probability of the next state given the current state is equal to the probability of the next state given the whole history. So I'll give like an illustrative example to explain what I mean by this, but basically all the information you need is in the current state. So if we had to think about examples of this, let's think about chess. So you have a chessboard. Essentially, if you have the representation of a chessboard, if you know where all the pieces are on a chessboard, you have all the information that you need to act. So if, for example, I knew what the chessboard looked like 3 or 4 moves ago, it's not really going to help me because I only need the current representation of the chessboard. It gives me all the information I need. So this is what we'd say is Markovian. Basically, you have all the information in the current state representation. But if we had to think about a different kind of, let's say, environment, if you're in this grid world, so imagine this is like a maze game, and you can't see the whole game. You can only see, it's partially observable, that's a technical term, but you can only see like a small section in the top left. What that means is it's not Markovian because you don't have all the information that you need. So if you only knew about that small block in the top left, then you're not sure, are you in the top left or are you in the top right, or you can't be certain where you are on the map. And usually for these sort of environments, what you do is you have history. So you have to remember where you were previously. So was I moving towards the left corner, and now I am sure I'm in the left corner. So these environments are not Markovian. So this just means the current state doesn't contain all the information. You need history. But we're going to focus on environments that are Markovian. And formally, an MDP is described using this tuple. And I'm going to just use like an illustrative example just to go through each of these properties of this tuple so that we're all comfortable with the terminology. So let's think of a simple maze game. So our agent is in red, and we have these, I would say, values or immediate rewards, and we have a goal in the bottom right corner. So firstly, we have this concept of state space, which is S. The state space is just basically a finite set of all the possible states that you can get. And what you do is you sample or you receive a state that's an element of that state space. So the state space represents all possible states you could be in, and a specific state is what your current, let's say, map looks like. So it gives you a description or a representation of the environment at a specific time. And this can be discrete or continuous. Discrete just means whole numbers. Continuous just means real numbers. And if we had to think about, let's say, our game over here, how would we represent it as a state space? You'd represent it, there's a lot of different ways you can represent it. This is just an example. We can use X to represent the agent. We can use T to represent the terminal or the goal. We can use B to represent things that are blocked. And we can use 0 to represent the open spaces. So formally, you just take your environment and give it a state representation that gives you a description of what your environment looks like. And now moving on to action space A. So you can see there's the arrows over there that represent the actions. The action space is, again, it's a set of all possible actions. And an action, so a specific action, is what our agent does. Again, this can be discrete or continuous, but examples of this would be 1 for moving left, or okay, I have numbers for both, but basically examples of this can be like 1 for left, 2 for down, 3 for right, 4 for up. So your actions can be represented again as discrete or continuous, but in this case, we're representing it as discrete values. So the actions is just what our agent does. And then we also have this transition probability, which is T. And what this tells us is the probability of transitioning. So if I'm in a specific state and I take this action, what's the probability that I'll be in S prime? So if the mathematics aren't immediately clear, I'll just explain it in words. So if our transition is deterministic, let's say you are on the map and you want to go left, then you can go left. It just means that the transition function basically lets you do what you want to do. But if your environment is stochastic, it means that you have a probability distribution over your transitions. So for example, if you would like to go left, you can maybe go left 50% of the time. Otherwise, you stay in your current location 50% of the time. And this is sort of just a transition probability function that tells you that what's the probability of transitioning given that you're in a certain state and you take a certain action. And then we also have D0 that just tells us the distribution of initial states. We're not going to go into too much detail there, but basically, do you always start in the same place, or do you start in different places across the map? And then we have R, which is our reward function. It tells us how good is our current state of action. So R is a function that's conditional on the state and the action. So if our agent over here is currently where it is, and it moves towards, I think that's right for where you're looking, it'll receive a reward of -1. So it's conditioned on where you are and what you do. And then we also have this discount. Again, this discount just tells you that it just penalizes rewards in the future. And it also has some nice mathematical properties, but it's not too important to worry about this discount. So currently we've gone through what an MDP is. And again, the symbols might be a little bit confusing, but it's important to remember that this is just a way of representing a sequential system. So if you have an environment, your environment would need to have all of these properties of an MDP. But this still doesn't tell us how our agents decide what to do. So this just tells us what our environment looks like. So next, I'm going to speak about a policy. So a policy can be thought about as the agent's brain. It's a mapping from perceived states to actions. The policy can be deterministic or stochastic. Again, I'm not going to go into too much detail there, but basically it's a function that you pass a state and then you receive an action out of it. So for example, if you're playing chess, you give this function a representation of the whole chessboard, and then this policy tells you what to do. So it tells you, I'm going to move my piece upwards. So this is what a policy is. You can think about it as the agent's brain or some sort of decision maker. And in deep RL, this policy is just conditioned by a neural network. So, sorry, not conditioned, it's parameterized by the weight of a neural network. So again, if we had to follow our agent across this map and see what it does, we'd build up this thing called a trajectory. And a trajectory is just the states and actions over time that our agent has done. So in the beginning, our agent was in state 0 and it took action A0. And then the trajectory is just the history of the states and actions that our agent took. So in this map, you can see that our agent moved, I think, towards the right and then moved down towards a goal. And the trajectory would just tell you what the state looked like and what actions our agent took each step of the way. And then we have a distribution over the trajectory. So what this tells us is if we have a specific trajectory, okay, so we have the policy over there. So pi is our policy. And the policy tells us if we're in a specific state, what action are we going to take? But what this specific trajectory distribution tells us is what's the probability of taking this trajectory. It'll be a bit more important in the next slide as to why we need this, but it just tells us if we have a trajectory, what's the probability of taking this trajectory, and we use the policy when making this calculation. So this sort of, I would say, goes to the crux of what we're doing in reinforcement learning. What is our objective in reinforcement learning? And this is actually, let's go back here. So this is our general objective in reinforcement learning problems. So this is what we're trying to optimize. Pi is our policy. So this is our objective for our policy. In purple, it's just saying we have our trajectory sampled from a trajectory distribution. So the trajectory distribution tells you what's the probability of specific trajectories happening. And then in orange, it tells us our essentially reward over time, the discounted reward over time for following these trajectories. So if I had to put this in plain English, if you want to maximize, you're trying to maximize the total discounted return per episode, but in plain English, if you're playing football, you want to score the most goals over the whole match. or over many matches. So you don't just want to score one goal, you want the reward over time. And that's what this concept of return is. It's a reward over time. It's discounted, but it's mainly important to understand that you want to know what's the best thing to do long-term in the future, and not the best thing to do immediately. So if we had to compare this return versus reward, so a reward tells you how good is your current state and action. So if I pass the ball now, this is how good my current state and action is, where return tells you it's the sum of rewards over time, discounted rewards. So I'm not going to worry too much about the discounted rewards, but it has some nice formulation. And also it encourages you to sort of get reward now as opposed to getting reward later, but you want the reward over time. And this is what is known as the return. So I've described the objective, what we want to do, what we care about, but I haven't described how we learn these things. So how does our agent learn to get better? And what mechanics or tools does our agent use to get better at certain problems? So in order to do this, we need to also know what a value function is. So what the concept of a value is it tells you what's good in the long run. So again, this might sound a little bit familiar to what we said about the return or the reward, well, specifically the return, but it tells you what is the expected return in the long run of a specific state. So if you had to think about the state value function, which just means this is a value conditioned, or it's a value for a specific state. This just tells you if I'm in that state, what's my expected return for that state. And then we also have the action value function, which tells you if I'm in the state and I take this action, what's my expected return. So again, to just try and make this sort of simpler to understand, so the value tells you, or the state value tells you, if this is what the game looks like currently, this is how good it is for me. So if this is what the game looks like, a high value tells you this is very good for me. A low value tells you it's very bad. Where the action value tells you if this is what the game looks like, and I take this action, so if this is what my football field looks like, and I run towards the goalkeeper, which is the action component, this is how good it is to do that. So the Q value function gives us a mechanism to see what is the best thing for me to do, because I can try different actions, or I can look at which actions would lead to the best return. And estimating these values is a critical part of reinforcement learning. So if we had to think about the different kinds of algorithms in reinforcement learning, there's a lot of different kinds of algorithms. And what we're going to focus on is Q-learning based algorithms. So these are, well, essentially, these are value-based methods, but we're going to focus on Q-learning. And this is about estimating what is the value of a specific state and action pair. And to understand how these algorithms work, we're going to have to use the Bellman equation. I don't have time to go through the derivation of this, so I'm just giving it here. I think the slides will include the full derivation of this, but basically what this tells us is that the value functions can be split into two parts. So it can be split into your immediate reward and your discounted value of the next state. So for example, if again, I'm going to use the football example, if you get an immediate reward for passing the ball and you want to know like the full return, you can say, the way you'd compute it is you say, what is my immediate reward for doing something? And then what is the future value of the new state and action that I would be in and the action that I would take. So if I am in this position, what is my immediate reward? And then after I take this action in the state, what is the value of my next state? So this is using the Bellman equation, and this splits the value functions into two parts. And if we split the value function into two parts, it makes us quite convenient for us to be able to learn these value functions. So this I'm going to speak about Q-learning. So Q-learning is about updating the value estimates based on other estimates. So I'd say it's about learning, informally, it's about learning a guess from a guess. So if we had to break down this equation, so this Q over here is the old estimates. We have this alpha, that's the step size. And then we have this target. So this target says it's a combination of your immediate reward plus your discounted reward. If you took this max action, what would be the Q value? So this max action is very important. This is what differentiates like Q-learning and what makes it offline versus online. Again, I'm not really going to go into those details due to time. But basically, this is the general process of how you update your Q values. So you have your old estimates, and then you have your target value, and you see how far away, or you calculate the TD error, how far away is your old estimates from the targets, and then you use the step size parameter. So it's like an iterative process. So if I had to quickly try and visualize how this would happen, is you would need to maintain this table. So this table on the x-axis tells you the different states, and then going down on the y-axis is the different actions. So you need to maintain a table that tells you if I am in a certain state and I take this action, how good is this action? So these are the Q values. This is known as your Q table. And this is essentially what you're doing in Q learning. You are updating this Q table, and you are using information from this Q table to make decisions. So in the beginning, maybe everything is initialized to 0, but as you iteratively move around in your environment, you learn, okay, certain actions and certain states are better. So this is what you end up doing in Q learning, in standard Q learning. And I guess if you're looking at this, it looks like a reasonable sized table. It's not that many states and it's not that many actions. But how would this work in a large state space? So if we had to think about, here we have 4 actions and 1, 2, 3, 4, 5, 6, and we have 6 different state space, but this is a very small game board. How would this work in really large states or action spaces? So this is a common environment in reinforcement learning. This is known as CartPole, and there's this sort of gives a description of the state space in CartPole, but the important thing to remember is that tabular RL, so what I just showed over here, this is a Q table, it does not scale well to complex problems. There's too many states to store in memory. So if you think about it, if here's this table, what if you have 100 actions and what if you have 100 states? Like this table would be massive, and it would be very difficult to store all of that information in a table. It's also too slow and to update the estimates for each value. So you need to have visited every point or have visited a lot of the points to update these values. So it's also quite slow if you use Q learning or tabular Q learning. So we need to use an approach to generalize across many states. So what we need to do is we can't just expect our, we don't want to just maintain this really, really massive table, because if we have a lot of states and actions, we need a way to generalize. And this leads us on to function approximation. So can we do dynamic programming with function approximation? So as opposed to maintaining this table, can we pass this information? So this is our state variables. Can we pass it to a neural network? And then the neural network tells us the values of taking different actions. So as opposed to us having to, as previously, keep track of this really massive table, what you can do is just pass your state information to a neural network, and your neural network will tell you the value of the different actions. So the good thing is, hopefully, if you have actions or if you have states that are close together, they'll have similar value representations. And this is what function approximation in, I'll go into more detail about deep Q-learning means, but this is essentially the main idea, is that we don't want to keep this massive table for states and actions because it's going to be really inefficient. And if you have, like, let's say, if you're working with images and you have like hundreds of pixels, it becomes basically intractable as a problem to solve. So what we do is we just use a neural network. And what this neural network does is it takes the state features. So in cart-pole, so this game over here, this is known as cart-pole. These are the features. So the cart position, the cart velocity, the angle of the pole, also the pole velocity at the tip. So all you do is you pass these features into a neural network, and then the neural network calculates the values, and you still use the TD error that we had previously. So you'd still use this TD error over here to calculate. It's just that now, as opposed to having a table, you're using a neural network to do this approximation. And then our target gives you the rewards to go. I'm not going to go into too much details about that, but basically a similar approach, but just using a neural network as a function approximator. So now we can go a bit into deep Q-learning. So this was, I would say, one of the first major breakthroughs in deep, I would say, deep RL. So this introduced like a lot of the, I would say this first deep Q networks paper, the playing Atari with deep reinforcement learning, was one of the first major breakthroughs in deep RL. And what they did in this paper is they said, okay, I'm going to take all of these Atari games and I'm going to feed in the raw pixels. So literally, if you think about a game, I'll show a video a bit later, just the pixels of what's happening on the game screen and across many games. And I'm going to feed it to a CNN. And this CNN is going to be the policy, or not the policy, it's going to be the value function that we are learning. So if you look closely, you feed in these raw images, and what you get as the output is you get the values for all the different states. So this is DQN, so playing Atari with deep reinforcement learning. And there was a lot of reasons why this was, I would say, a major breakthrough. I would say the major ones was because they were able to use the same algorithm across a lot of different games. So whether it's Pong or there's a lot of different sort of Atari games, so able to convert all of those games into images and then have the same algorithm and the same agent learn these value functions. So this is an important aspect of deep RL, where we use a lot of the breakthroughs. So this was CNNs. We use a lot of the breakthroughs from deep learning in order to handle and represent either the value function or the policy. And this is essentially what makes deep RL or deep learning different from standard tabular RL. We're using function approximators. So to get this deep, to get DQN working, there was quite a few tricks. I'm not going to go into all of these details, but I'll go into a few of the main ones. So the problem is in standard Q learning, the data is sequential. And that is non-IID. So if you think about it, when you're working in supervised learning, your data should be IID. That just means that it should be independent, right? So whether your data is at the first point or the second point, it shouldn't matter because the examples should be independent. But in DQN, this was not the case. Well, in DQN, you actually, or in reinforcement learning, the data isn't IID because if you think about Pong, you have the representation of the game here. And if the pixel or if the ball goes upwards, that would be your next state. So it's not independent because let's say where the ball is now is related to where the ball is going to be next. So this concept of IID, it broke down in deep Q networks, and they used this thing called experience replay. So what they did is they said, as opposed to sequentially looking at the states in my trajectory, I'm going to mix those states up. So this is just experience replay. So the target networks helped with having like policies that were more robust to change with the Q values, but I'm not going to go into too much details. But basically, they use deep Q learning, and they had to implement quite a few tricks to get it working. But when they did get it working, they were able to see that their algorithm was able to get human level or above performance on a lot of different games. So this is across a lot of different games. And this is obviously the first deep RL breakthrough. So obviously now, if you look at the results, there's a lot more results, but it's able to do well in a lot of different games. I'm going to try and quickly see if I can play the video. Oh, okay, the video is already playing. But basically here, this is showing Pong. And it's showing that after, I think, 100 training episodes, it was able to do well. So this is the learning process that happens in RL. Your agent controls the paddle board. In the beginning, it's not doing that great. It's just trying to slowly get better. Let's wait for this video. 400 training. It's slowly getting better. It's improving. And then hopefully at the end, we'll be able to see like a nice little trick that this agent managed to learn. So this is 600. So it learns this new strategy called tunneling. So it learns that it's best to actually hit the ball to the edges, and then the ball goes and just bounces around, and yeah, it bounces around and it hits the other obstacles. So it found a strategy that wasn't necessarily expected. And this is, I guess, the main benefit of using reinforcement learning, is that you don't necessarily have to give examples of how you want the agents to behave. All you do is you have to give a simulator, and then you give a reward function, and then your agent can learn these like arbitrarily different behaviors across different kinds of environments. So this is essentially the thing that really separates RL from supervised learning. Supervised learning, you have an expert or a teacher that tells you what to do and tells you what's good and what's bad, looks like a cat, what looks like a dog. In RL, you give the reward signal, but you don't tell it how. So you don't tell it what policy to follow. And if you think about it, it's possible to do that. So in chess, it's possible for you to look at the chessboard and see if this is a good position or a bad position, but there's a lot of different strategies, and you don't have to know all of the strategies. Your agent can discover all of these different kinds of strategies. So this is, I would say, just the first early breakthrough in deep RL, and obviously after this, there've been a lot of breakthroughs, but they follow the same principle, where combining deep learning, where you have representations, and reinforcement learning, where you learn through interactions, and combining the two so that you're able to learn across a lot of different challenging problems. And then I would say for next steps, if maybe you enjoyed this talk and you want to know what to do next, in the Deep Learning Indaba, we had a reinforcement learning practical. So if you go, I'll share the slides and you can click on the link. But there's a reinforcement learning practical where you'll go through the basics of reinforcement learning. You'll see how to interact with an agent. You can take actions. And then eventually at the bottom, you'll learn how to implement your own Q learning agent. So you'll actually learn from a code principle how to implement these methods. And yeah, that's essentially all I wanted to chat about. I know that maybe it's a lot of content and a lot of information. And if you didn't get the symbols, don't worry. After a while, you get comfortable with that sort of layout. But yeah, hopefully this was useful and interesting. And yeah, I'm open to any questions relating to RL or anything in general. I'm just gonna stop sharing my screen so that I can see the audience. Okay, I'm just looking in the chat. Is a table of cumulative rewards that the agent has gotten. So yes, this is the table that the agent slowly updates over time. So in the beginning, if you think about it, our agent doesn't know how good any of the actions in the states are, but eventually, iteratively, if you use a Bellman equation, so if you say how good this state and action is depends on my immediate reward and what my next reward is, what you eventually do is you keep on, this is called a backing up. So you keep on sort of moving through states, and then you eventually have all that information backed up. So is a table like cumulative rewards that the agent has gotten? It's not rewards, it's the value, so the expected return. So it's basically like, if you had that table, what you would say is, if I am in that state, so if I am in this state, if I move up, I'll get a plus 100. If I move down, I'll get minus 1,000. Okay, so then let me move up. So it tells you how good each action is if you're in a specific state. Is there a comparative study for the results from RL for tabular and other models for tabular data? So yeah, I think it's also just important that to distinguish the difference. So in RL, when I say tabular RL, I'm not necessarily meaning tabular data, like in terms of like supervised learning, you have tabular data. So when I say tabular RL, it just means that your value function, so how good everything is represented in a table. So it's more about the representation of your value function. It's not about tabular data, because if you think about it, in this, let's say in the football example, it's not tabular data. It's an agent kicking a ball and then seeing what reward it gets after kicking the ball or interacting. So it's important to understand the difference between tabular RL, which just means your value function is tabular, versus tabular data and supervised learning. Yeah, those are just two different things. And yeah, I understand the wording can maybe be confusing. But yeah, it's a bit different. Comparative study from the results. But again, like if you were to like go through the DQN paper, you'll see that before DQN, it was very difficult to get neural networks working on environments. So they had to implement a lot of different tricks, but they also performed exceptionally well across a variety of different problems. So I'd say that is the main paper if you want to get into deep reinforcement learning. And deep reinforcement learning, like I said, it's not just something for games. It's something that you can use if you can formulate your problem in a way that can be used on like a simulator. It's a possible way to solve a lot of different kinds of problems. And I know in this IndabaX, the focus is like moving beyond the hype. And I think that it's important for us to understand that reinforcement learning has had some hype, but there's a lot of practical applications. And like I said, if you can formulate your problem in an environment, reinforcement learning is a very good technique at solving problems where you don't know all the possible solutions or ways of solving the problems. So another question, I'm guessing it's computationally intensive. What sort of systems running? Okay, so yes, standardly deep reinforcement learning is computationally expensive, and there are ways, there's like a lot of new methods where they've been able to learn a lot faster, and they've like learned models, and there's a lot of tricks to make deep reinforcement learning faster. But the main premise is that you learn through trial and error. And if you learn through trial and error, unfortunately, it does sometimes take a lot of time, and you need to scale your algorithms to get good results. But there's a lot of work on like efficient reinforcement learning. What sort of systems have you deployed on? So yeah, like I said, at InstaDeep, we use reinforcement learning as one of our core technologies. So a data bun, the train project. If you have like a lot of trains, yeah, that's essentially, I don't know if my time's out. Okay, so it's like if you have, like for data bun project, you have a lot of trains and you need to schedule these trains. So that's like a system that we haven't deployed it, but we've got it working on the simulators right now.
Okay, so there's one question here. So if you can kindly.
Yeah, thank you very much. So with regards to the discount factor that you spoke about, you made us understand that the discount factor belongs to a value range of 0 to 1. But then in practice, what is the optimal value? Because a 0 means that much importance is given to the immediate reward, and then for a 1, it means that much importance is given to the future reward, which is so unrealistic. So in practice, what is the optimal value that is mostly used? And then I also want to ask about the Kale-learning, and then the SARS. I understand that it is used for temporal difference learning. So what is the clear practical solution for solving MRDPs? Thank you very much.
Sure. So I'll answer, yeah, the first question is a very good question. Yeah, unfortunately, a lot of the time, the discount factor, the community does have general discount factors that they use. So like 0.99 or 0.95. But sometimes it's something that you would have to sort of play around with trial and error. So I'd say like the default from like a practitioner side is 0.95 or 0.99. But sometimes, like you said, depending on the weighting, it can have different effects. So it's about thinking about your problem and thinking about how important is it for you to get the reward immediately, and how important is it for you to get the reward in the long run. So it's essentially a hyperparameter of your problem. And I think it's important to just think about it. How does it make sense in your current problem context? And to think about, do you either want to encourage immediate rewards, or do you want to encourage rewards much further out in the future? But yeah, the default we tend to use is either 0.99 or 0.95. So that's the first question. The second question, I'm not sure if you could, so you're asking how can Q-learning be used to solve the MDP? Just to clarify that second question.
I want to know how Kale-learning, and then I know that Kale-learning and SARSA are used for temporal difference.
So the whole process.
Yes, but then when you want to work with large scale data sets, is it required that you'll be working with Kale-learning?
Yeah, yeah, I think I get the question. So I'll try and answer it, and you can maybe give me some feedback. So yeah, so again, Q-learning is one of the approaches. I think in one of the slides I showed that there's value-based methods, so Q-learning, and we focus on Q-learning, but there's also policy-based methods. So instead of learning the value, so how good things are, you can learn the policy directly. And then there's also actor-critic methods that combine value-based and policy-based. So in RL, there's like a whole list of different algorithms, and depending on the configuration of your environment, you can use different algorithms. So currently, actor-critic is the best sort of general field of algorithms. So things like PPO perform quite well. So I would say there's a lot of different algorithms, and you can use them according to your problem. But in terms of having, let's say, large data sets or large environments or state and action space, that's the point of sort of doing deep Q-learning. It's a point of having, instead of a table, having a neural network represent your value function. And if you have a neural network represent your value function, then you can represent, sorry, I think I had like power outages. You can represent your value function in a more efficient way. I don't know if that answered your question.
Yes, please. You did.
Okay. Cool. Do we have any other questions?
Okay, looks like there are no more questions. Okay. So thank you very much, Khalid.
Cool. Thanks so much for having me. Yeah, it was great to be here, and hopefully everyone managed to learn something. I'll share the slides, and you can follow on some sort of like more detailed explanations for some of the derivations if you're interested. But yeah, thanks for having me. Oh, I do see there's another question. Can you say there's no data available? I'm not sure if I have time to answer that. Deborah, can I?
Yes, you can take the answer.
Okay, cool. So yeah, so reinforcement learning, I would say, is very good for problems where there is no data. But again, you still need to create some sort of simulator to behave like an environment. So if I had to give, like, let's say the train problem, we had to create a simulator where that behaves like different trains and has different maps. So it's good for problems where there is no data, but you still need to create the simulator so that your agents can do like trial and error and sort of learn from interacting with the environment. So it's kind of, can you get labeled data, or can you create a simulator and then your agents learn from that simulator, or like a virtual environment? Cool, I think that is it. If that is all the questions, thanks again. It was really great to speak to everyone, and hope everyone enjoys the rest of the conference.